Hello students, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 2 of a unit Magnetism and Matter. So let's begin with today's class. In today's class we are going to discuss about the magnetic induction. So let's begin with the magnetic induction. So first we will look at the force acting on the poles of a magnet in uniform magnetic field. So let's first assume for the North Pole. So for the North Pole, by conventions, we considered it as a positive monopole, and South Pole we considered as a negative pole. So if we have a convention from the electric charges, the plus q having a direction, a plus q charges would be there, then the direction of electric field be in positive x direction, and it is moving from radially outward, while if negative charge was there, the direction of electric field was radially inward. So same thing is true here, same thing is true here as well, that this is, if this is a positive monopole, it's a north pole, then the direction of magnetic field is radially outward from the north pole. And for the south pole, the direction of magnetic field, the direction of magnetic field is from radially inward. So for the north pole, force acting on the north pole is directed along the field, it is in the same direction, in the same direction along the field. But for the south pole, force acting on the south pole is directed opposite to the field. So let's find it out, the magnetic induction, or when we say magnetic induction we mean it's a strength of a magnetic field. Strength of a magnetic field can be expressed in terms of a vector quantity that we call as a magnetic induction, that we call as a magnetic field B. If I want to denote it, if I want to denote it in terms of the magnetic force, then we can say that the magnetic induction of an external field at any point in the magnetic field is defined as the force experienced by a unit positive, please have a focus on this word, x as force experienced by a unit positive north pole kept at that point. So the magnetic field B, that should be is equals to F divided by M, and this is the vector quantity. I hope this is clear. If you remember, this is the same thing when we used to have electric field E, then we used to call it, it's an F divided by Q. Yes, it's a electrostatic force divided by charge Q, and this was Newton per coulomb. It is the electric field, this is the magnetic field, both are the same thing. Look at this, here charge is there, here mass, here the magnetic strength is there. I hope this is clear, is it? So please always have a comparative analysis, have a comparative study like this, because this will help us to revise and to remember the things over both the units. Please, this is very good approach to remember the things simultaneously of two concepts, two different fields. Yes, so let's understood that what would be the strength of magnetic field due to single pole. Let's suppose a magnetic induction at any point due to a single pole M could be calculated as this is B is equals to mu naught by 4 pi into M by R square. The situation could be something like this. Let's suppose this is North Pole. One more thing, one more time, I make it clear that we are understanding that only a monopole do not exist, but on a hypothetical analysis we are considering that if that do exist, the all the situation would be look like this. Yes, so for the north pole, let's say this is positive pole, and at this point I want a magnetic field, the separation between this two is the R, then I can have this B is equals to mu naught by 4 pi into M by R square, where M is the pole strength, R is the distance, R is the distance of a point from the pole, and to find out the direction, of B at any point, we have to place a unit north pole at that point. So for the north pole, it is always directed away from the north pole because this is positive. So this would be moving in this direction. And for a south pole, let's look at this. It's a south pole. Let's suppose this is the location where you find out, where you want to find out the magnetic field. This is the distance r. And for this, the direction of magnetic field will be in this direction. So it is always directed towards the south pole. I hope this is clear. So, for a monopole, magnetic field could be written as B is equals to mu naught by 4 pi into m by r square. Now let's work for the magnetic induction. Magnetic induction at a point on the axial line of a bar magnet. So what axial line is? When we say it's let's suppose this is south pole, this is north pole, and if we are on this line, we are on the same line on the axis of the magnet, then this could be considered as the axial line. Yes. So when we want to find out the magnetic field due to axial line, it could be B is equals to mu naught by 4 pi into 2 into m into t divide by d square minus l square whole square. I'm pretty sure that you have derived it in your school classes. So here we are just doing the direct formula of this. Even we have derived this in the first unit electric charge and field, so you can take the help from that lectures also. So this is the magnetic field on the axial line. So for a short bar magnet, this could be written as mu naught by 4 pi into 2m by d cube. And the direction of magnetic field B is along the axial line and from the south to north pole of a bar magnet. So this is south pole, this is north pole. This is the direction of the magnetic dipole moment, and this is the direction of magnetic field B. So as I can see that these two are in the same direction. And from this I have one more relation, that magnetic field is inversely proportional to the cube of the distance if m is constant. So I could write it's b1 d1 cube equals to b2 d2 cube. I hope this is clear. Is it clear? Is it clear? Great. Next, magnetic induction. Magnetic induction at a point on equatorial line of a bar magnet. So let's suppose this is south pole, this is north pole, and you want a magnetic field at point P, which is on the equatorial line. So if I want to derive it, I am having an B is equals to mu naught by 4 pi multiplied by m upon d square plus l square to the power 3 by 2. And if it is considered as a short bar magnet, then that could be written as B is equals to mu naught by 4 pi into m by d cube. Direction of the magnetic field on the equatorial line is opposite to the direction of magnetic moment. So magnetic moment is in this direction, and this B is in this direction from north pole to south pole. If m is constant, I can have the relation which is equals to magnetic field is the cube of the, or I could say it's an proportional to the cube of the distance. It's an inversely proportional to the cube of the distance. So I can write it's a b1 d1 cube is equals to b2 d2 cube. Does it clear? Are you sure? So let's summarize this two situations on the axial line and on the equatorial line. The situation would be that this is, let's say, south pole, this is north pole, and you require to find out a magnetic field over here. This distance is r. So as this is south pole, this is north pole, so this could be written as magnetic moment m, I should say magnetic dipole moment, and this should be the direction of magnetic field B. So here the magnetic field on the axial position is mu naught by 4 pi multiplied by 2m by r cube. Yes, and one more thing, it's an angle between m and b is 0, so they are on the same direction. This is the first case of the axial position, and when I write this relation, I am considering that it is a short dipole. So this is first. Now the second, for the equatorial position, it is for the equatorial position. While I write this for the equatorial position, I must understand that this is the south pole, this is the north pole, this is the point P where magnetic field is required. This is the distance r. So when I write this, I could write it's B is equals to mu naught by 4 pi multiplied by m by r cube. The direction of this is in this direction, it's an m, and direction of B net will be in this direction. So it's an angle between M and B is 180 degree. They are opposite to each other. I hope this is clear. Is it clear? Is it great? So let's suppose if someone has asked me that suppose this is the bar magnet, it's a south pole, it's a north pole, this is midpoint, and from this is P1, and the separation is R, and the another location, this is P2, even this separation is R. This separation is R. Yes. So what they want, find out ratio of first magnetic field at P1 to the magnetic field at P2, second magnetic field at P1 to the magnetic field at P2. Yes. So how could I do this? What I understood using this is, first magnetic field at point P1, let's assume this as a short bar magnet or short dipole, I'm sorry. So when I assume that this is the short dipole, we can write this as the mu naught by 4 pi multiplied by 2m by r cube. And for the second magnetic field at point P2, it is equals to mu naught by 4 pi multiplied by m by r cube. So if I want to take a first ratio, this is B at point 1 to the B at point 2. This is equals to, if I take a ratio of this, I will be having, it's a 2 is to 1. It would be a 2 is to 1. And if I take a ratio in a vector form, while I take a ratio in a vector form, it means I also need to calculate, I also need to consider the direction. So while I consider the direction, this is south, this is north, so this is the direction of magnetic moment. When I consider the magnetic field at point P1, this would be the direction of first field, it's a BP1, and this should be the direction at magnetic field at point P2. So if I take a ratio of this two, this would be minus of 2 is to 1. Does it clear? Does it? Are you sure? Yes. Great. Now let's work for the next question. Let's suppose they ask that Let's suppose this is the situation. This is South Pole, this is North Pole, and when I say this is South Pole, this is North Pole, this is the midpoint, and this is the point P. This separation is R. I hope this is clear. We have one more bar magnet which has been kept like this. This is South Pole, this is North Pole. Even this separation, even this separation is R. Yes, this separation is even R. So what they want is find out magnetic field at point P. This is requirement, that find out magnetic field at point P. How will you do this? Take your time of 30 seconds and just check that how should you do this. Yes, anything in your mind? How shall I do this? Let's have a look that this is South Pole, this is North Pole, and the direction of magnetic moment, this direction of magnetic moment, let's suppose this is first magnet, this is second magnet. So this is south, this is north, this is M, and for this point this is the axial point, so magnetic field due to this first would be in this direction, because for the axial position the direction of magnetic moment and direction of the magnetic field will be the same. For the second magnet, this is south pole, this is north pole, so this is the magnetic moment. And when magnetic dipole moment is in positive y direction, its magnetic field in the negative y direction. So this is B2. Let's write down the magnitude of B1 and B2, as B1 is the, yes, we consider this all are the short dipoles. So magnetic field due to first it's a B1 that is on the axial position could be written as this is equals to mu naught by 4 pi multiplied by 2m by r cube, and for second it's a B2 that should be is equals to mu naught by 4 pi multiplied by m by r cube. Is it clear? Now one more thing, that these two are in perpendicular to each other, these two are in perpendicular to each other, and when these two are perpendicular to each other this could be written as B net, that should be is equals to root of B1 square plus B2 square. And when I say it's a root of B1 square plus B2 square, this could be written as mu naught by 4 pi multiplied by m by r cube root of 4 plus 1. So this is equals to root of 5 multiplied by mu naught by 4 pi multiplied by m by r cube. This is B net. That's it, you did it. Great job. Is it clear? Is it? So can you do this? Can you do this? Are you sure? Can it be done? Can it be? Great. Let's work for the next question. Suppose the situation is that this is the first magnetic moment M, and this is the second magnetic moment M. This is the angle that is of 120 degree. Now Let's suppose from here at an angle bisector a certain point P is there. At an angle bisector certain point P is there, which is at distance r from this. As I said, it is an angle bisector, so this angle should be a 60 degree. So the question is find out magnetic field at point P. This is required. You need to find out magnetic field at point P. How will you do this? How this is supposed to be done? How this could be done? What do you think? What what I understood is that this is one of the magnetic dipole moment. This is another magnetic dipole moment. If I take a resultant of this two, if I take a resultant of this two, what it will be? Let's have a look. That this is one of the dipole, it's an M. This is another dipole, it's an M, and this is at 120 degree. So if I find out the resultant, it would be equals to 2 into M into sine of theta by 2 or cos of theta by 2. What it would be? Yes, it is a cos of theta by 2. So it's a mr is equals to 2 into m into cos of theta by 2. This is equals to 2 into m into cos 120 by 2. This is cos 60 degree. And while I say cos 60, it's a 2 into m into half. Could be written as m. I hope this is clear. Yes. So the situation will be now. The m resultant would be in this direction. So we have one more magnet, or I should say, if I want to replace this two magnets with this single magnet, it is m. It is m something like this. Yes. From this is at location r. So this could be said as that this is at the axial position of this resulting magnetic moment. So when I calculate the magnetic field at point P, what I can have is that B is equals to mu naught by 4 pi multiplied by 2 into m divided by r cube. My m is again m, so this is equals to mu naught by 4 pi 2m by r cube Tesla. This is magnetic field B. I hope this is clear. Is it clear? Are you sure? Are you sure? Great. Any doubts? Any issues? Anything? Is there anything which could not be understood? Anything? No? Great. Let's look at one more result, that magnetic field due to magnetic dipole moment at any point P. It's a magnetic field due to magnetic dipole moment at any point P. So this is the situation. This is the north pole. Sorry, this is the south pole. This is the north pole. And if this is the south pole, this is the north pole, then this would be the axis, and this is the direction of M. From this, we are making certain angle theta over this. This is theta. So magnetic field at point P could be written as mu naught by 4 pi multiplied by M by r cube. This is separation r under root of 1 plus 3 cos square theta. Does it clear? Does it clear? Is it? Are you sure? Yes. So this is magnetic field at point P. If it was the case of an axial position, then this theta should be equals to 0 degree, and if it is 0, this cos 0 would be equals to 1. So this could be written as mu naught by 4 pi into m by r cube under root of 1 plus 3 cos 0 1. It's a 1 plus 3 4, 1 plus 3 fours. If I take it out of the square root, this would be the 2. So this is equals to mu naught by 4 pi into 2m by r cube. And if it was the case, if it was the case of equatorial position, then this would be theta would be 90 degree, and when it is 90 degree, this cos 90 would be 0. So that could be written as mu naught by 4 pi multiplied by m divided by r cube. This is the magnetic field at equatorial position. So does it clear? Does it clear? Are you sure? Are you sure? Any doubts up till now? Anything? Is there anything? No? Great. So this is the magnetic field at any point P. Now let's just find it out. Torque acting on the magnetic dipole. This all are the theories. This all are the theories that we have covered in the last unit, moving charge and magnetism. So you must remember each and everything based on this. You must remember each and everything based on this. I hope you understand this. Yes, so we are just having a brush up kind of thing because NCRT has written a certain segments in the moving charge and magnetism and certain segment in the magnetism and vector. That's why we are covering it on the both the sides, because question can be asked from any one of the point. Yes, so let's check it out, which is the torque acting on the magnetic dipole. The situation is, let's suppose this is the direction of magnetic field. This is the direction of magnetic field B, and from here we have put one of the magnet over here. Let's say this is south pole, this is north pole, and if this is taken as a reference axis or reference line, I can say this, then this is the magnetic moment M, and this would be the angle theta, so that we have the relation that this torque would be equals to M cross B, and magnitude wise that can be written as torque equals to M B sine theta. This is the torque. This torque could be written as mb sine theta. I hope this is clear. Is it clear? Is it? Are you sure? Great. Next, let's check it out, that potential energy stored in magnetic dipole. So what we are supposed to do is that this was the situation, that this is the magnetic dipole B, and let's suppose this is the situation. This is south, this is north. From this is M, and this is angle theta. Initially it has been angle theta. Yes, and then work done by magnetic field can be calculated as mb cos theta final minus of cos theta initial. We understood that work done is equals to minus of change in potential energy, so that could be written as, that delta U could be written as mb into bracket cos theta initial minus of cos theta final. So this is U final minus of U initial, that should be is equals to mb into bracket cos theta I minus cos theta final. So for a potential energy, we take a reference. For a potential energy reference, PE is always 0. So to get reference potential energy as a 0, the theta initial would be equals to 90 degree, and if theta is initial is equals to 90 degree, U initial would be a 0. That means final potential energy would be equals to minus of mb into cos theta. So we are having two relations. One of them is delta u, that should be is equals to mb into bracket cos of theta initial minus cos of theta final, and another, it's a u final or u only, that could be written as minus of mb into cos theta. I hope this is clear. Yes, these two are the relations for the potential energy. For the torque I am having the relation which should be is equals to mb sine theta. Always the theta is the angle between magnetic moment m and magnetic field b. So if I take a ratio of this u by torque, that should be is equals to minus of cos theta by sine theta. It's a cot theta. So this potential energy divided by torque would be equals to cot theta. Got it? Got it? This is the relation that we have used in the these are the relations that we have also used in the previous unit. Here one more time, we that's why only we are discussing this. Let's have some questions based on this, that find out change in potential energy when bar magnet is being rotated from from 45 degree to 60 degree when it has been placed in uniform magnetic field. So you need to find out a change in potential energy. So for the change in potential energy, I am having delta u, that should be is equals to mb into bracket cos theta initial minus cos theta final. While I say this delta u is equals to mb into bracket cos theta initial minus cos theta final, I could write it as this is equals to m into b into bracket cos theta initial from 45 to 60, it's a cos of 45 degree minus cos of 60 degree. This could be written as mb into cos 45, it's a 1 by root 2 minus cos 60 1 by 2. So this is equals to mb into bracket 2 minus root 2 divided by 2 root 2. This is change in potential energy. This is change in potential energy when this has been rotated from 45 degree to 60 degree. Does it clear? Does it? Are you sure? Are you sure? Yes. Let's move for the next question. The question says that if dipole, or I should say if bar magnet has been rotated for 45 degree, energy stored in it is 100 joule. Find out torque acting on the bar magnet. Find out the torque acting on the bar magnet at this position. How will you do this? How this could be done? So what they have given is, the when it has been rotated for 45 degree, that means initially initially I hope the system was look like this. This was the power magnet and it has been placed like this at 90 degree, and after that it has been rotated like this, that this makes an angle of 45 degree. So what you need to do is this u is equals to minus of mb cos theta, and this is a torque which is equals to mb sin theta. Let's let's just take a ratio of this potential energy, it's an 100. This is torque. This mb has gone, and this is minus of cos theta by sin theta. It's a cot theta, and the theta is 45 degree. So we understood that cot 45 is equals to 1. So this torque equals to minus of 100 Newton into meter. I hope this is clear. Is it clear? Is it clear? So can you do this? Can you do this? Are you sure? So can it be done? Can this be done? So let's wind up this session over here. This is all about the magnetic field, or I should say a magnetic induction. We have discussed magnetic induction due to monopole, due to dipole on its axial position, on its equatorial position, and at on the any position at point P, which makes an angle theta with the magnetic dipole. Then also we calculate the torque acting on the magnetic dipole, and magnetic energy or potential energy stored in the dipole when it has been rotated from certain angle theta 1 to theta 2. So you must be clear, you must be very clear about all these points, about all these topics. I hope this is clear. Yes, so please do as many questions as possible. Please revise it once, twice, or thrice. Yes, this will help us to score good numbers. Thank you. Have a good day. Take care. Bye bye.